And we are recording. Welcome to SLiTHER number 30. I can't believe it's been 30 of these so far, but they've been great. Today we're going to do a little bait and switch, and surprisingly enough, this is a good bait and switch. I'm probably not going to talk at you too much, which is better for everyone. We've got a special guest today, Madeline Radlauer, who is from San Jose State, and she's going to talk about CBC. I might chime in a little bit, but we're going to be talking about covalent bond classification. Before we do that, Madeline's going to tell us a little bit about something coming up related to DEIJ issues. So I'm going to turn things over to her. Only saying, if you have any questions, please feel free to interrupt as we go or throw them in the chat. I will be monitoring the chat and doing my best to get those fed in as we go.
Thanks. And I hope everybody will chime in as they see fit, whether it's with comments, questions, or, references to Groundhog Day, which Chip promised, and I tried to deliver. So hopefully we'll get through that. So the DEIJ thing that I'm presenting, I actually have two things I wanted to let y'all know about. So one is at San Jose State, we have a campus reading program where we send a book out to all our freshmen. This is pretty common practice, so maybe I'll do this too. This year, the book was called Citizen: An American Lyric by Claudia Rankine, and it is a beautiful poetic work on being, I think she might say it a little differently, but the way I read it was, it's about being a Black woman in America and that experience of it. And so we were looking for ways to relate this to science and to our science students, and came up with a program that's coming up on February 9th and is open for registration. So if you're interested, follow up with me and I'll send you the registration link, or you can look at it on our SJSU website. It's sjsu.edu/reading. So there it is. But it'll be a discussion on inequity in medical practice by three fantastic and brilliant women, and moderated by a member of our School of Nursing. So check that out. The other thing that I would like to mention, so I'm on the WCC, the Women Chemists Committee National Committee, as an associate member. So not a voting member yet, but this year is the 95th year of the WCC, and so there are a ton of programs coming up over the course of the year, and I just, there's a plug to kind of keep a lookout. There's going to be I think a big announcement at the beginning of March, and stuff associated with like both the ACS national meetings this year. So cool. Should I just go ahead and jump into the SLiTHER material? Sweet. Let me share again. All right. So covalent bond classification, I decided if I was going to be chatting with a bunch of educators, we should start with some learning objectives. So at the end of the SLiTHER, you should be able to count electrons using the CBC method, be able to make an informed decision on whether to use CBC in your course, have examples of when and how to introduce CBC to students at the undergraduate and graduate level, and recognize a few places students might get confused. So that's a lot for a very short period of time. And so I'm depending on your background, your strong background knowledge in that, but also we'll post some things, and eventually I will get some things as LOs to the website as well. So what is the covalent bond classification method? This is a method to classify ligands in transition metal complexes, and it's a really useful tool for electron counting for these complexes. But there's also a lot of terminology associated with this that can confuse students. And so and we're going to start in with terminology right away. It's also known as this neutral ligand formalism. And that's how I was taught it, the neutral ligand formalism. I didn't hear about CBC actually until much later, but it's the same thing. And maybe this makes sense as a name for it, because what we're going to do is consider the ligands as neutral species, but it's not the only way to do this. You can consider ligands as ionic species, and so that could be considered the oxidation state formalism. I like to think about the reason that we use CBC, or one of the compelling reasons to use CBC is it allows you to think about where the electrons actually, quote unquote, come from. And so Chip actually pointed me to this reference and and this image in particular, and I really like it. But basically, if the electrons are coming from the ligand and being shared with the metal, then this is an L-type donor. If the two electrons in the bond are coming, one each, metal and ligand, then this is an X-type donor. And we could kind of think of that as a more traditional covalent interaction, but that's a little weird. And you'll see why in a minute. And then if the electrons are coming from the metal and being shared with the ligand, then that would be a Z-type donor. So here's another way of just calling it. So the L-type is a 2-electron donor. X-type is a 1-electron donor. And the Z-type is a 2-electron acceptor. And the reason I have donor and acceptor in quotes here is because sometimes an L-type donor and X-type donor is much more electronegative than the metal, usually, actually. It's more electronegative than the metal. And so it's not really like giving the metal those electrons, it's using them in the bonding framework. And that can be a point of contention for students, and one that is kind of tough. Another piece that is potentially confusing is that ligands can have multiple bonds with metals, meaning that they're a combination of LX and Z. So we might have like an eta-3 allyl, and that would be an LX type ligand, and an ethylene diamine, or that would be an L2 type ligand. So here's this like point of potential confusion if you don't directly address it. LX and Z classification is not directly related to electronic classification that we use to consider ligand strength. So pi donor, pi acceptor, and it's not directly related to electronegativity. So this idea of saying that L type is going to be a 2-electron donor can really confuse the heck out of students. And I haven't figured out a great way of stopping that other than just like saying straight up, hey, we're going to say that these 2 electrons are coming from the ligand, but it's not coming from the ligand and going to the metal. It's coming from the ligand and contributing to the bonding framework of the complex, not like giving it away. And that helps, but yeah, more comments on that, highly welcome. When I talk about ligand types, after I've introduced them, I give out this handout, and we'll share this with the SLiThEr. I have that like caveat right at the top. This handout does not classify ligands as sigma donors, pi donors, or pi acceptors. And there's no easy way to correlate. And I give some, places where it might, it might conflict with their initial idea. Like the X-type donors can be pi donors or pi acceptors. L-type donors can be sigma donors only, or pi donors or pi acceptors. So it's all kind of, don't use this handout to try to do that part of the class. That seems to have worked this year. So I remade this handout this year, and that like putting it right out front and saying this is not that helps. But again, yeah. So in terms of common ligands, I give them this handout, and then I tell them, don't use this handout other than to like help you. Take the ligand off the metal and consider it as a neutral species and see how many electrons it has to donate. If it's going to have a lone pair, you draw your Lewis dot structure and it's got a lone pair, it's L-type. If it's got only a single electron, like a chloride might have a single electron, then it's X-type. And if it doesn't have any electrons to donate at all, then that might be a Z-type. And then if it's got multiple groups, then we might start to think it in more complicated terms. So I encourage them to use this handout to check their work rather than to go through and like memorize and do assigning, because that actually doesn't get them there very far. So let's take a couple of examples now here, because that's always more fun. And take the ligand off the metal as a neutral species. Lewis dot drawings of the ligands can be really helpful. So these are actually the 2 examples that I bring up in the first, in the recorded lecture that I have. So I flipped my course, or semi-flipped my course. And so the recorded lecture has this one first. And I encourage them to actually like go through the process of taking the ligand off the metal. So if we want to take the chloride off the metal, the chloride has that single electron, and I'll point to it in red, that makes this an X-type ligand. And point of confusion, they're like, yeah, but it has other electrons too. It also has lone pairs. And so I have to remind them, like, well, are those in a good position to also donate to the metal? You know, what do we think about the relative electronegativity? Does it want to share those electrons? And sometimes it becomes easier later in the course to convince them of that after they've started looking at the molecular orbitals and the relative energies of the atomic orbitals, to say, like, okay, these lone pairs from the chloride, they're not going to donate into the metal, and they feel good about that. And then we also have the amine. There we go. So 3 of the electrons from nitrogen are bonded to the hydrogens, and then we've got 2 electrons left, making this an L-type. So this is one that I think is a little more straightforward. So I purposefully gave them one that isn't very straightforward as our second case. And so in this case, we first look at the smaller ligands, because that seems easier. So this nitrogen is bound to 1, 2, 3 things. So 3 of this nitrogen's electrons are bound up. Those dots were not intended to be electrons. They were my counting. But the key being that this nitrogen has 2 electrons left. So the pyridyl nitrogen then can be considered an L-type donor. And similarly, we can go through with the methyl group here, and there's only 1 electron left on that carbon, because 4 valence electrons, 3 with the hydrogens, so this becomes X-type. All right, and then we've got this thing. I actually made this complex several times when I was a graduate student, which is part of why I really like to use it as an example. But I also like to use it as an example because it looks intimidating. And I want them to see something that looks scary that I think actually turns out to be a pretty easy example. And so if we take this phenoxyimine off of the transition metal, we've got an aryl group here. So let's start with the nitrogen. The nitrogen has 3 things bonded to it, which means it has 2 electrons left over and can be L-type. And then the oxygen has only 1 thing it's bound to. So that means with 6 valence electrons, it's going to have 2 lone pairs and then 1 single electron. And so we're going to call this X-type. And so overall, the phenoxyimine is LX. So one of the places where students tend to get a little nervy about this is, again, they say, okay, but that oxygen also has 2 lone pairs. How do I know those lone pairs aren't getting involved? And so one of the things that I'll mention is, well, we're only drawing a single bond to the nickel, between the nickel and the oxygen. So if we're only considering a single bond, which one of these, is it going to be the single electron or the lone pairs? That helps a little bit. And then, we also talk about how does oxygen usually bind? Usually binds to 2 other things. Thinking about its relative electronegativity, those types of things can help the students feel more comfortable with these ideas. Okay, so now we've assigned our XL and LX, right? We have the chlorides are X types, as same with the methyl. The amine is an L type. The pyridine is an L type. The imine is an L type, and the phenoxy is an X type. All right, so if I go to the next slide, I'm going to have to clear all of that. your first Groundhog Day reference, make sure your students are like taking it easy with this. Sometimes a deep breath goes a long way. Now, something in the chat. Single electron and one pair, and a one pair on a donor atom that they use. I don't think there are examples where they might use a lone pair for binding before a single electron. I can't think of any off the top of my head. If anybody has one, shout it out. But I think you'd always use that single electron first. And that seems consistent with our understanding of stability. And so, all right, so once we've gone through and we've actually said, okay, we've got L-type and X-type ligands, and notice I didn't give you any examples with Z, and I highly recommend that you don't give students any examples with Z. Once they get comfortable with it, it's okay to drop one in there, but like, don't put it on a test. That's mean. But yeah, it's definitely something that I tend to stick with L, X, and combinations thereof. So you've got your ligands classified. To be able to count the electrons for a complex, we also have to consider the metal and how many electrons there are for the metal. And so we're going to use, like, later in this, I'll use a little m to consider the number of valence electrons on the metal. And basically, it's just the group number. So titanium gets 4, and iron gets 8, and nickel gets 10, right? So we get to use that. All right, so with that in mind, we can now put together this designation, MLXZ with Q+. And so let's define all those terms real quick. So the first is M is just the metal. Keep it as M when you're drawing out the designation. L is for L-type, just keep it as L. But then little l is our number of L-type ligands. So we're going to put in that value. Big X indicating X-type, and the little x indicating how many. So put in that value. Z-type and how many Z you have. And then Q is for the charge. We'll get to charge in a minute. But let's go ahead and just take what we had here. So we said that the chlorides are X-types and the amines are L-types. So I would call this an M L2X2. And it's neutral, so I'm not going to worry about Q. And then in this case, I have my metal, and it is also 2 L-types, right? Because I have the pyridine and the imine, and 2 X-types because I have the methyl and the phenoxy. So these complexes look really different, but they're both group 10 metals type, with the designation of ML2X2. So they have more similarity in terms of CBC classifications than not. All right. This is going to be a bunch of terminology. I mentioned there was a bunch of terminology. I figured I'd share it. So we often talk about our 18 electron rule, similar to the octet rule, but with a lot more exceptions. An electron count of 18 is often favorable for transition metal complexes. And this comes from the total number of electrons that can fit into the sp and d valence orbitals. So total of 9 orbitals, 2 electrons per orbital, we get 18. But there's a lot of exceptions. Then we can start actually talking about the terms for the counting and what we want the students to determine. So the valence shell electron count, also known as the electron count, also known as the electron number, and also represented in some cases by En, which is not electronegativity, which really confuses me. So I actually never use that. But the term valence shell here can be confusing because the next term, one of the next terms I'm going to tell you about is valency, and then students equate the two incorrectly. So what is it? So you got little m, which is the number of valence electrons on the metal, which is equal to our group number. Then we've got 2 times the number of L-type donors, 1 times the number of X-type donors, and then you subtract Q. Oh, I like that idea of using VEC instead of EN, so valence electron count. Nice, thanks, Adam. So that's the formula. Basically, it's the sum of the electrons on or shared with the transition metal, and it only includes the electrons that are involved in the sigma bonding framework. So to to kind of build on that, if you have a pi donor ligand, the electrons that are donated by the pi donor don't get counted in this. And so that can be a point of confusion later on. Ligand bond number. Oh, by the way, that pink thing, I don't tell students that up front because it just adds a level of confusion that is, but when we get a little later and we start learning about pi donor ligands and they're like, wait, the electron count doesn't seem to match this, that's when I say, but the electron count is only counting electrons that are involved in the sigma bonding framework. So I wait till later to share that tidbit. So ligand bond number is the number of L type, the number of X type, the number of Z type. So total number of ligands surrounding the metal. You have to count each moiety that binds. So an LX type ligand would contribute 2 to the ligand bond number. So reminding them that if they do the designation first, this works, but they shouldn't just count the number of fragments or molecules attached. All right, so have an asterisk on both oxidation state and valency here. Oh, coordination number. I've heard that too. I didn't for ligand bond number as another terminology there. I can add that into the slide before we post them. All right, so oxidation state of the metal. This is going to, L-type ligands don't affect the oxidation state. And so we'll, X, we're gonna have how many X plus 2 times how many Z plus the charge. Then we've got formal charge on the metal center. We can call the oxidation state a formal charge on the metal center. The valency or valence number has the same formula, and we can consider it as the number of electrons a metal uses in bonding. And the reason that I define these slightly differently is because of what happens when you have metal-metal bonding, which I'll cover 2 slides from now. And then finally, the D count, or DN metal configuration. So you can take the group number of the metal and subtract the valence number or the oxidation state. These are usually the same, except when you have metal-metal bonding. The number of electrons, and we can define D count as the number of electrons in the 10 primarily D-based molecular orbitals. All right, so students tend to forget about Q when they're doing oxidation state and valency calculations, and actually under all circumstances, they forget about the charge if we have a charge complex. So I'll chat about that in a second. I really liked this image from the parking group where they show how well the 18 electron rule works. So looking at the range of compounds, the percent of compounds with different electronic configurations. So 18 and 16 are the most common across the periodic table, all transition metals, but there are others, and that's important to recognize. All right, I'm gonna catch up on the chat for half a second. Okay, cool. So let's actually go through and count the electrons for this now that we have it. So we said that this platinum complex is an ML2X2, and we know that M in this case is 10 because platinum is a group 10 metal. We have 2 times the number of L, so 2 times little l is going to be equal to 4, and 2 times little x is going to be equal to 2, making this a 16 electron complex. The oxidation state, remember, is just from the X type, the Z type, and the charge. We have no Z type, we have no charge, so it's really just how many X type ligands we have. So the oxidation state equals 2, or 2 plus. And then the valency, or the valence number, we don't put a charge on the valence number either. So the way we represent it is usually just how many electrons. So it's just a number without a particular charge. So the platinum is using 2 of its electrons in the bonding framework. And then our D count, our DN, is equal to the group number minus the oxidation state or valency, and that's going to equal 8. So I would call this a D8 metal. And we could go through the example with the nickel, but it turns out that all of them are exactly the same because this is, again, and Ml2x2, where the metal is group 10. So the answers are the same. All right. What about Q? I love this reference. Chip mentioned it, and I was just like, yes, we have to do it this way. TNG. All right, so I wanted to give a couple examples of charged complexes. So here we have a negative charge on this platinum complex. And so we start with platinum. This is how I typically write it out. 10 electrons from platinum, group 10. We've got the chlorides, which we know already are going to be X-type donors. So 3 chlorides is going to be 3. And then we have our ethylene. And our ethylene is binding with, through its pi system. That doesn't mean it's a pi interaction, but it's binding through its pi system. So that's 2 electrons being shared with the platinum. This is an L-type. And so the ethylene is going to give us 2. And then you might look at this and say, I have 15. That seems like a weird number, but we don't want to forget Q. We have a negative charge here. So if we have a negative charge, that means more electrons. And so -1 is going to add 1 to our list. So we get a 16 electron complex. This also is going to affect our oxidation state on the platinum, or our valency on the platinum. So remember that you're going to take X plus Q, and Z would be in here as well, but we don't have any Z donors or Z-type ligands. So X plus Q, it means we're going to have 3 plus -1. So the valency in this case is going to be 2. And this is a pretty common valency for platinum. So I feel, pretty good about that. If we look at this ruthenium dibenzene complex, then we've got ruthenium, which is group 8. We've got the 2 benzenes. Each of them I'm going to count as an L3 type ligand. And so 2 times L3 would be, so each L3, that's going to be 6 electrons each, right? So you can just say 2 benzenes. Like I said, this is the format I typically draw it in, but you can amend to your preferences. And then we've got a +2 charge. So positive charge means fewer electrons. So 2 plus is going to indicate -2. And we get an 18 electron complex. So finally, I've given you an example of an 18 electron complex. Realize it's taken a while. All right, so an advanced topic here, I'm gonna erase this so you can see this, is this idea of an equivalent neutral class. I don't typically teach this in my undergraduate class because it's a point of potential confusion. But basically, we can theoretically compare complexes as neutral complexes, right? If we take the charge and fold it into the ligand types. I'll let you play with that a little bit. But the purpose behind the equivalent neutral class is this. There are trends from this equivalent neutral class designation and valency. And you can actually see that for each transition metal, there is an MLXZ plot available for group 3 through 10 first, second, and third row transition metals, where it shows you what the most common types of complexes are. And so for platinum, maybe not surprisingly, this 16 electron valency of 2, Ml2x2, really, really common. The rest, not so much. And so this, I find this really interesting. And you see that you have some cases where you have a platinum 0 and some cases where you have a platinum 4. But really, those are the oxidation states we're seeing, or the valencies we're seeing. So. Metal-metal bonds are a special case. I like to introduce them to my undergraduate class as well as to a graduate level course. Count electrons for each metal separately, so you don't over or undercount electrons based on those that are in the metal-metal bond. And you can treat the metal-metal bond as an X-type ligand. which will work on everything except oxidation state. And what's kind of cool is it brings up some interesting questions about D counts that people who get excited about inorganic chemistry can kind of dig into a little bit more. So that's fun. So I have one example, this rhenium. So I'd count one rhenium at a time. And I'm going to consider, so rhenium is group 7. I'm only going to consider the stuff that's bound to this one rhenium. So I have 5 carbonyl ligands. A carbonyl ligand, if you take it off of the metal, is going to have, and draw a traditional Lewis dot structure, is going to have 2 electrons. So this is going to be L type. So that gives me 10. And then I have this bond to the other rhenium, so that if that's an X type, then that gives me 1, and I have an 18 electron complex. Funny thing is that if I'm treating it as X type, for valency, I would say that this is a valence number of 1 because it's sharing an electron with this other rhenium. It's using an electron in bonding. But with oxidation state, just like, dioxygen, you don't consider the oxygen as having a formal charge. The oxidation state is going to be 0. And so if you define D count based on oxidation state or valency, you get different numbers. And what does that mean? And which one is correct? And how do we know? We can talk more at length on that. But I'm looking at the time. I want to make sure we cover a few more things, because I've said we'd talk about why choose neutral ligand versus oxidation state formalisms. So with the example of a cyclopentadienyl ligand, you have 5 pi electrons donating into our metal center. So we count this as 5 electrons. This is an L2X type ligand. With an ionic interaction, the cyclopentadienyl will be negative, and we would count that as 6 electrons. The oxidation state on the iron is the same in both cases, an iron 2+, and we get a D count of 6, which is good, because that's what how we would consider that when we do the molecular orbital diagram. The issue with the ionic version is that this isn't really iron 2+ Cp-. And on top of this, like, students bring up some misconceptions about solubility and polarity. If you, it takes the 1 electron counting method and fixes it. I really think so. CBC is superior in many ways because it allows you to do predictions about the complexes, I think, a little bit better. And it actually makes it a little simpler for students, because when they're not familiar with a ligand and whether it will be charged, I know you can take it like off as closed shell, and then some, usually students do okay with it, but they lose track, I think, a lot more easily than just saying, just make it neutral and see, and count that way. So I'm a big fan of CBC. I wouldn't use anything else. I used to tell them about both, and then I just stopped telling them there were other options, because it became a point of confusion. And I can give more partial credit if everybody's doing the classifications by CBC. If they get the classifications right, but then like mess up later on with oxidation state, I don't worry about it. All right, so when might you bring these up in your courses? For an inorganic undergraduate course, I actually split my MO theory into 2 sections. So compounds where you're only looking at S and P orbitals, and complexes where D orbitals are really important, the frontier orbitals of transition metal complexes. So I do electron counting for transition metal complexes right in the middle, so that they see electron counting, and then we go into when the D orbitals are frontier orbitals in your MO diagrams. For a graduate organometallics class, I start with electron counting, because whenever we learn about organometallic reaction steps and mechanisms, for example, like oxidative addition, I'm like, time to count electrons again. So we always do that first. All right, how to assess it? So I think it's, because it's very puzzle-like, you can be creative with it. I love the d orbital game. I actually keep this on my desk because it actually has CBC ligand classification in it. It's amenable to a skill check type problem. So you can do like a really simple, can you count the electrons, or can you classify the ligands? But you can go really deep. There are a lot of fun, challenging things that can be done. So predicting which complexes will form or be more stable based on an expectation of how many ligands might bind. We could use them electron count to predict whether a dissociative or associative mechanism might be preferred. And I do that one in undergraduate in organic. And then predicting how a ligand with multiple potential binding groups might bind a specific compound, or you could do literature-based problems, especially once you get into an organometallics class. So it goes on. And I want to finish here because I feel like cyclopentadienyl ligands are like always on some problem on an exam I give. So here we go. You want a prediction? It'll have a cyclopentadienyl ligand. All right, so I know I went a little longer than we usually do for the chat. I hope this was helpful to folks, and I'm really happy to continue the conversation that's going on in the chat or what have you.
Thank you. Thank you. That was awesome. We had some things in the chat. Is there anything anyone wants to bring up here or question a little bit more? Go ahead, Anthony.
So, Madeline, I just want to thank you because you said something on slide 16 about the equivalent neutral class, and that screws up my students every single year. And I love the formulation that you talked about by incorporating Q or the charge into all of the calculations. That is going to simplify for my students because it's always, I always feel like that they can get L and X, but then when they have to go for a charged complex from that classification to the ENC, they constantly screw it up. And then everything else is wrong, right? You know, and so that was really excellent.
Well, and I would say too, so one of the things that I'm trying to make sure I do on any assessment of this is I give them credit for classifying the ligands first. And then so then if they mess that up, it's going to mess everything else up. And so I just try to, if they're consistent from there forward, I give them the credit. That way it like, you know, decouples. But yeah, absolutely. Equivalent neutral class. I only teach that at the graduate level now. And I've only done the organometallics course here once because we don't have enough faculty to consistently have an organometallics class. But I think that that's a fun one there because you're getting into some of like the theoretical pieces, and having these charts, right, can be really, really, oh, did I like go the wrong way? I did go the wrong way. Having these charts can be really helpful for somebody actually studying, you know, organometallics literature and reactions, but it's not necessary for the first inorganic course. Yeah, Adam.
I want to amplify something I put in the chat when I was talking with Anthony and Kyle about ferrocene, but I also wanted to say that somehow I missed when I teach this, and I taught this last week, right, that you remove the ligand as a neutral species. Like I still always think of the X ligands as anions, and I probably say that, which is why my students are confused, right? But you remove it as a neutral. I mean, that's so obvious, and it's in the instructions, and I wrote that down. I'm going to tell my students. And I'm going to tell my students to watch this SLiTHER, so hi, students.
And that's one of the problems with this. You know, we always refer to them as chloride ligands, and hopefully somewhere along the way, they weren't. Oh, chloride, that's Cl minus.
Yeah.
Yeah. Well,
I wanted to. Oh yeah, go ahead.
No, I was going to say like that idea of a fragment. Like, I think when you say take it off as neutral and just draw the Lewis dot structure, it gives them an opportunity to like grab onto something they feel really comfortable with. Potentially, hopefully, and they can say like, oh, a Lewis dot structure, I can do that, and they'll draw that. So I always have like one like really wonky giant ligand example where if they just go through and they look at only, so there are 2 points that could become confusing. So if they just look at the things that are binding to the metal, they do just fine. Sometimes when you give them a larger ligand, because you're like, oh, I just want you to see that it's actually simple, they'll try to bind everything in that larger ligand to the metal. So if we like go to, for example, the phenoxyimine, it's only the oxygen and the nitrogen that we're going to consider in the electron count. And so that's the other piece that I think sometimes raises confusion, because they're looking at it and they're saying, well, but there's this aryl group, is that going to be L3? And here's this other thing, is that going to be, you know, a terbutyl, is that going to be an X type? And you're like, no, only the things that are binding to the metal. So I think that emphasizing that the electron count itself, the valence electron count, I like VEC. You said that, right? That's really useful. The valence electron count is only what's going on either from the, like, electrons from the metal or directly bonded to the metal.
So the thing about ferrocene, I just wanted to amplify this so it's recorded. So Kyle asked about coordination number versus ligand bond number, and I'm sure I got this from you, Chip, but for me, ferrocene, you have 10 carbons within the same, they're all the same distance from the iron, so the coordination number is 10, right? There are 10 equivalent carbon atoms, but that isn't helpful or realistic. We don't want to think of that as being a 10 bonds to carbon. There's 2 ligands, so the other possible coordination number is 2, and that's also not very good. So ligand bond number is how many orbitals from the metal are being used. So XLL, that's 3 orbitals, and then XLL down. So you've got 6 orbitals, and then ferrocene becomes an octahedral complex, you know, with a twisted axis system. But that, so I really try to differentiate ligand bond number versus coordination number. And then for simple ligands that don't involve pi bonding, then coordination number and ligand bond number are the same, I think, in almost all cases.
I don't know that I've written that definition like that, as the ligand bond number is the number of orbitals from the metal used in bonding, but I really like that. That makes sense too.
Do we have any other questions? Or Kyle, in the chat, you had something about this cleans up the one electron issue. Do you want to?
Yeah, so I've always been an IONiC person.
Well,
myself,
we all are as part of
IONiC, right?
Yeah.
Because one of the things that the problems that I've had with the neutral version, because they all do it, is the oxidation state. Because then they treat all of the X-type ligands as neutral without accounting for the, because they just think, oh, it's neutral, not thinking, you know, that the X versus L. And so, you know, so then you get people saying ferrocene is iron 0 with, and, you know, and it's not. And so, yeah, that was one of the big things. And then, of course, then you have the 1 or the 2 electron counting. Which one do you do? And then, so that's why I always like the IONiCs, is like 2 electrons for everything. You know, just count the things. Is it 2? You know, like, but yeah. So I think I like how this is cleaning up the 1 electron thing. Which, you know, some students I teach both in both my junior senior level inorganic and my graduate master's organometallics. But then I tell them, like, I use IONiC. You can use whatever you want as long as you do it right. Right. Yeah.
I started out doing that, like saying use what you want, and that did not go over well with the undergraduates. And so I tell them, like, there are other ways to do this, but we're going to do this way because I think it's the simplest and I think it's going to teach you the most. And I actually haven't had the issue where people see an X-type ligand and then say it's neutral. Like, actually, oxidation state is something they feel really comfortable with. So I don't know if that's actually something that I've seen as a hang up. Maybe I've just gotten lucky. I don't know.
So like you, Kyle, I was a very staunch IONiC person for a very long period of time. And the ferrocene iron 2 thing was what really sold me. You know, like why I wanted to be IONiC. It's like, it's iron 2. But, you know, then with some conversations with Jed, and, you know, he does this much better than I do when he teaches it, because he does magic tricks while talking about it, which makes it fun. But you know, just sold me on the idea of, okay, this makes so much more sense. And I think kind of one of the places my students hit a little bit of struggle with this sort of thing is when you look at the chemistry too much. You know, I have to remind them constantly, like, this is a bit of a formalization, and we are looking at state functions here, right? yes, you added an H plus to a metal, but it doesn't make it a Z ligand when you count it at the end of things, right? You treat it as an X because that's what it is. When you make ferrocene or a CP complex, yeah, sure enough, the reaction, you might have used sodium CP to make it, but you're still going to treat it in counting as an L2X type ligand. Yeah. Anyone else have any other comments? Adam's got something he wanted me to bring up that's been floating around on the Discord, but I want to make sure anyone else has a chance to bring up any points.
I'll just say that because of all of your work on this chip, I am definitely a full CBC convert, and I'm changing all my handouts and removing the IONiC method and the covalent method. I'm just doing CBC now, so it's taken me a while. I'm a slow learner.
That's awesome. I think it helps for me that I was taught CBC first, and then when I was in grad school, one of my best friends had done his undergraduate research with Jed, so it was yeah, there it is.
So one
exactly.
of the things floating around on the chat was, and Madeline kind of touched on this a little bit, the idea of, you get pi donors, pi acceptors, and there are some ligands out there that are just the devil. Jed's got some really awesome in-depth in some of those resources that we had posted there. Nitrosyl is one that is just a beast. Oxos are crazy. You can think about them in a number of different ways. They can be Z-type ligands. They can be X2. You got to be really, really careful with some of those and think about them. You mentioned the metal-metal bond kind of situation and how you deal with that. There's a great, Jed's got a great piece on the FIP dimer, the CP iron dicarbonyl dimer, and how the bridging form of that doesn't actually have a metal-metal bond, even though people tend to draw it with one, and how that affects counting. So, yeah, because I just had that Zane's sitting in my backyard ready to go. Not all of us live in Chicago and could possibly get there easily, Kyle. But there's a lot of subtle nuances on there, but if you keep them, I think Madeline did a great job of giving us simple yet complex ligands. I mean, those are big ligand systems, but when you do come down to them fundamentally, they are, just L and X. Yeah, you can go out of your way and find these nasty, horrible beasties out of there, but you don't have to. Go, Kyle.
Yeah, so I was going to say the kind of doing the nasty stuff, the can be done after you've done some things. So I try to keep counting pretty straightforward and simple. And then for one of my problems I like to use in both inorganic and organometallics is I give them a cobalt-3 methyl complex, and then I have I draw the product, 3 different products. So cobalt without the information on the cobalt, methyl plus, methyl radical, and methyl minus. And then they have to do the arrow pushing and the oxidation state changing. So again, I'd say okay, when you're doing the counting, it doesn't matter how it got there, but now let's talk about what happens when things react, right? And so then they have to think about what's the difference between methyl X, methyl plus, methyl neutral, and methyl minus coming off of a metal. I should probably make an LO for that one if I haven't already.
That would be awesome.
Go, Anthony.
Well, so I always try to keep my example simple, but I ran into an example last year where there was a paper where they redetermined the crystal structure of a Werner complex that was found in an archive, that was made 100 years ago. And it has a bridging superoxide ligand. And I said, oh yeah, well, that looks really easy. But when you look at it, if you draw the superoxide, each oxygen has two lone pairs and a single electron in its neutral form. But then when you actually do the electron count, it has to come out as an LX ligand for everything to make sense. And so then I'm sitting there like, well, where the hell does the electron go? And then why does it use a lone pair on one, but a single electron on the other, right? So like, I thought it was this simple like O2 ligand, right? And like all hell breaks loose, right? So it can get complicated, and it's like, oh my God, like what have I just done?
Yeah, that's a good moment to like make sure that you've written the key before you give the problem.
And maybe talk yourself out of using that as the problem.
I do actually show that paper and that structure, but I only use it when I'm talking about Werner and how like it's good to keep good records because you can go back and it's like Werner from Beyond the Grave. I think Lippard's on that paper, and Byrne, who's the Bert's Byrne.
Yep.
Yeah, the person.
That's the one.
Yeah. And it's the scheme where it's like 1,500 grams of something or other, and then like leave it in a bowl in a windy place. Like it's great. It's a great paper to show.
I'm not familiar with it. I need to see that.
I'll post it on Discord.
Thank you.
Yeah.
I'll go find it and post it on Discord, and I'll
on
tag you.
It's on Viper. It's Werner from Beyond the Grave.
Yep.
Werner from Beyond the Grave. I love it.
All right. Any other questions or comments? If not, Madeline, thank you so much for stepping in and doing just a super job of leading us in our SLiTHEr here. We
thank you
had some great conversation, and hopefully some people pick up some of this and use this as a resource. And I think I have to announce that there's another SLiTHEr coming up in about 2 weeks, and maybe Kyle or Matt was smart enough to look at the schedule and see what's coming when. Well, about 2 weeks. The announcements will be coming out on Discord, Twitter, Facebook, and all the other platforms we do those, but expect one here soon. But with that, I will say happy Groundhog Day, even though the little rat saw a shadow today. So 6 more weeks of winter.